Okay, this is the key to test 3. I'll do all 3 choices, and remember you only had to choose one. The first one, we had f of x is x plus 2 over x plus 3, or equivalently, y equals x plus 2 over x plus 3. To find the inverse, we're first going to switch x and y, and then solve for y. And to do that, we're going to multiply both sides by y plus 3. Remember, we're solving for y, so I want to get the y terms on one side and the non-y terms on the other side. And to combine these terms, we simply factor out what makes them like. We get y is 2 minus 3x over x minus 1, and that is our f inverse. Roll this up a bit here. There we go. That's a little bit better. Okay. There's the solution to the first choice. The second choice has us finding the inverse of a simpler function. Again, this is the same as y is 2x minus 4. And so we switch, and we're going to solve, which is really straightforward. So we get that f inverse of x is x plus 4 over 2. Now here we're asked to verify or show that f of f inverse of x is x. So we'll start with f of f inverse of x and see what we get in the end. That would be f of x plus 4 over 2. Now f, remember, doubles our input and subtracts 4. So we're going to double the input and subtract 4. Well, those cancel. And we're left with just x. So the two parts would be the verification and the computation of f inverse of x. Now the last one seems more complicated than it is. We're looking for an inverse for f of x is x squared, and obviously the problem with f of x equals x squared is that as it is on its natural domain, it doesn't have an inverse. So we're going to restrict the domain. There's a number of ways to do this. The two obvious choices are greater than 0, and I'm going to choose that one. Maybe we can call that f of x is x squared for x greater than or equal to 0. Just capital F. And we can see that this graph passes the horizontal line test. And the inverse of it, in this case, would be the square root of x. And again, you can calculate that, but it should be fairly straightforward that the positive root of f of x, this is the positive root of x, and again the negative root of x would be down there, which would be the reflection of the other branch. And so we'll say that the domain restriction is x greater than or equal to 0, and the inverse on that piece is the positive root of x. Okay, in the second problem, we have to solve either of these. Again, we'll do one at a time. I'll do 2 to the 1 minus 3x equals 5 first. And the simplest way to do this is simply to rewrite this logarithmically. And now we can subtract 1 and divide by negative 3. There's our solution. For the one over here, 1 minus 2e to the x equals 0.2. We're going to first want to solve for e to the x. To do that, we're going to subtract 1, divide by negative 2, and now we're going to rewrite this logarithmically, or equivalently take natural log of both sides. Okay, let's look at the next page. Okay, these questions again. I'll do this one first. I'll do B first. 22 plus 5 times the log base 10 of x equals 7. We'll have to do that. We're going to first isolate this log. Remember, the range of log x is all real numbers, so there's no problem having the log of x be a negative number. We just can't take the log of a negative number. Now the second one, ln of 2x plus 10 equals 4, is already a single logarithmic expression, so we can write this as 2x plus 10 equals e to the 4th. And subtracting 10 from both sides and dividing both sides by 2 gives our solution. Now these next ones, again, there's a couple ways to do each one. I'll start with this one first, and we've seen a few like this. The first observation is that this is e to the x plus 12 over e to the x equals 7. And I'm going to let w equal e to the x because I can see it repeated a number of times here. And to solve this equation, I'm going to multiply the left and the right sides by w. That is the effect of w squared plus 12 equals 7w, or in standard form. And nicely enough, this factors. And the solutions are w is 3 or 4. Now remember, w was e to the x, so if e to the x is 3 or 4, we still need to solve for x, and that's just a matter of rewriting this logarithmically. Natural log of 3 or natural log of 4. Now the first one I'll do over here. 2 to the x plus 1 equals 3 to the x minus 1. Now there's a couple ways we can solve this. The simplest way, I think, is to take the log of both sides, and you have choices. Log base 2, log base 3, natural log, and log base 10. And I'll just go ahead and do natural log because a lot of people did choose that. So the natural log of the left-hand side equals the natural log of the right-hand side. And so the left-hand side becomes x plus 1 times the natural log of 2, and the right-hand side becomes x minus 1 times the natural log of 3. Now this equation is linear in x. Notice the x is just multiplied by various numbers and added up. So we have x ln 2 plus ln 2 equals x ln 3 minus ln 3. And we can do this, for example, by getting our x terms, this one and this one on the same side, and I'll bring them over here. So x ln 2 minus x ln 3, and the terms that don't have any x's, we can move to the other side. Minus ln 3 minus ln 2. And to combine these up, we can simply factor out the x. And now dividing both sides by the coefficient of our variable. There's our solution. And it can be written different ways if you had chosen to, say, use log base 3 or log base 2 or log base 10, but it would be an equivalent answer. These next ones, again, here are some logarithmic equations, and I'll do this one first. Here we have log base 10 plus log base 10 equals 1, and we know we can write that as the log of the product minus x and 3 minus x. equal to 1. And so now we can change this to an exponential equation. And so we get minus 3x plus x squared equals 10. And in standard form, after factoring, we get x is 5 or negative 2. And then we need to check when x is 5, I've got the log of negative 5 up here, and the log of a negative is undefined, or at least not real. Whereas if x is negative 2, then that number's fine. That's the log of 2, and that's the log of 5. So our only solution is x equals negative 2. Now this equation over here works in a similar fashion, except notice the minus there is going to lead us to write the log base 2 of the quotient. So converting to an exponential equation, we get 2 to the first power. And we can solve this by multiplying both sides by x minus 1. And subtracting x from both sides and adding 2 to both sides, and we get that x is 3. Okay. Next page. Okay, both of these we're going to use our calculator. And since it's probably likely we're going to use this function more than once, I might as well go ahead and enter it in. So it's 72 minus 42 e to the minus 0.04311 times t, or x in this case. And we're going to want some things. What is the initial temperature of this drink? Well, again, the input is the time in minutes, and the output is the temperature of the drink in degrees Fahrenheit. If we went to a table, and I'm going to turn my table set to ask, typed in 0, we get 30. And so A of 0 equals 30 degrees Fahrenheit. Remember to write the units. You can write 30.0 degrees Fahrenheit, but this is still accurate to the nearest tenth. What was the temperature of the drink after 1 hour? Well, after 1 hour, it's 68.8 degrees Fahrenheit. And again, 1 hour and 60 minutes. When will the temperature reach 65 degrees Fahrenheit? Well, to do this, we need to solve the equation. 65 is 72 minus 42 e to the minus 0.4311 t. We can do that algebraically, or we can do it in our calculator. And I'm going to go ahead and solve this in our calculator first. Now, I don't know the time involved, but I know my window could be from, say, 0 to, let's make it 2 hours, and I'm going to use Zoom Fit, Zoom 0. So there is my warming drink, and 65, there it is, a horizontal line. And I know that this is the temperature of the drink as it warms up. It was a slushy. And second trace intersect. First curve, second curve, guess. 41.6. And so one of our solutions would be 41.6 minutes. Now we can do that algebraically. We might as well go ahead and do it algebraically. To do this equation algebraically, we could subtract 72 from both sides, and we would get minus 7 equals minus 42 e to the minus 0.04311 t. Divide both sides by negative 42. Take the natural log of both sides. And then divide by both sides by the coefficient of t. And we can check that this number should be the same. So we have the natural log of 1 divided by 6 divided by minus 0.043111, 1, and 41.6 to the nearest tenth. So we get the same answer. Now, what is the temperature of the room? Well, one way to answer this is to look at the temperature of the drink as time gets longer and longer. Say 2 hours, 3 hours, 4 hours, 5 hours, etc. 6 hours. And you can see it looks like it's getting closer and closer to 72 degrees. And just to be absolutely sure, you can put in 1,000 hours maybe. And you can see after 1,000 hours, the drink is actually at 72 degrees or so close the calculator can't distinguish the difference. So this is actually the limiting value of A, or horizontal asymptote, but I'm going to say A of larger and larger numbers, or times in this case, goes to 72 degrees Fahrenheit. Okay. Now the second problem, we're given this radioactive decay model, and again, P is the initial amount, K is a growth or decay constant. In this case, it's decay, so K will be negative. We want to know K to the nearest millionth. Okay, and if we started with 500 grams and ended with 401, then we know that 401 is 500 e to the, and the time involved was 32 days, so it would be K times 32. We can solve that in our calculator, but it's just as easy to solve it by hand. So the natural log of 401 over 500 over 32 will be K. I skipped a step there, but let's see what we get. The natural log of 401 divided by 500 divided by 32, 0.06895, etc. to the nearest millionth. 1, 2, 4, 6. It would be 0.06895. So there's our value of K, and we can check the sum of the digits. 6 plus 8 plus 9 plus 5 does equal 28. Now, how much fermium will remain after 30 days? This was K is approximately minus 0.006895. And for this, we want to know what is A of 30. And we'll go ahead and we can do this by hand. And in this case, I'll just go ahead and write out what it is. It's 500 e to the minus 0.006895 times 30, which is approximately some quantity, and we'll calculate that. .406.57, and we want to know this to the nearest integer. So that would be 407 grams. And the last one is this half-life. And again, this value of K goes up here. The half-life to the nearest integer. And to solve the half-life, I'm going to fit it in here. If we started with 500 grams, then the half-life would be the amount of time it takes to end up with 250 grams. And that's the equation we need to solve. And in a very similar fashion, we're going to get natural log of 250 over 500 over minus 0.006895 is T, which is approximately something. We'll go ahead and calculate that. So we have the natural log of 250 divided by 500. There's the 1/2 divided by minus 0.006895. We get 100, and to the nearest integer, it would be 101 days. That's the answer to that one. Okay. So that's the end of the response section, the multiple choice section. Okay. The first question is the inverse of x cubed. We should know that the inverse of a power of x is a root of x, and the x cubed does have a full inverse. That is, it's a one-to-one function across its domain, and its inverse is the cube root. You can verify that by checking their graphs or running a few numbers. This is a base 10 logarithm. We know the logarithm's inverses are exponentials with the same base. Base 10, and if you look on your calculator, you should see right above the log key, you see its inverse 10 to the x. Right above the ln key, you see its inverse e to the x, in case it's difficult to remember the basis. Which of the graphs below is a one-to-one function? Well, remember, one-to-one passes a horizontal line test, and although this one passes a horizontal line test, it's not a function. The only one that is a function that passes a horizontal line test is D. Now, number 4, we have this function graphed here, and the idea is to find its inverse. We're going to reflect it across this line, y equals x. And the reflection across this line should give us a curved portion up here, something like that maybe, and then a linear portion down there, if you can imagine that. So it's going to be this curved portion will appear up here, something like this, and then this ray will reflect to give us a ray like that in the downward direction. And you can see the only one that fits these criteria is A. Number 5 is a to the b equals c. So we would write it. The base is the same, so it would be either this one or this one, and it's log base m of t equals p. Okay, and again, another one. The base here is e, so we know it's going to be e squared equals a plus b. Now, for those people that have the newer operating system on their calculators, you can do this directly, but the old way just works just as well. And it would be log of 7. And this one would be the log of 7 over the log of 5, or the natural log of 7 over the natural log of 5. Either of those would give you the right answer. We can check that the log of 7 divided by the log of 5, 1.2091, and the natural log of 7 divided by the natural log of 5 is the same number, 1.2091 to the nearest 10,000th. This next one asks us just to evaluate an expression. It's fairly straightforward. The natural log of 1 plus the square root of 2, close the square root, close the natural log. That's my numerator, divided by 3. 0.2938 to the nearest 10,000th again. Now, number 9 asks us what the log of x over the log of 2 is. And if you remember the change of base formula, this is the change of base, this expression. Now, one student had an interesting method for verifying which of these it is. If it holds true for all x, then it holds for x equals 5, for example. So let's check, and this is one student said, well, I'm going to evaluate this expression, log of x over log of 2, when x equals 5. Let's see what happens when I evaluate all these expressions when x equals 5. So the first one will be log of 5 divided by the log of 2. 2.3219. 2.3219. Now, to calculate this, you would very quickly find you were doing the same thing. That one is the same. Let's just check that when x is 5, we don't get this one. So the log of 5 minus 2, well, that's 0.477. And how about the log of 5 minus the log of 2? And that's 0.397. That doesn't match. And of course, it does match this one. So that's an interesting technique. And again, we can try it on here. Let's go ahead and see on this one. And you might check to see that this can be written in some ways. You can write it as the log of x to the quantity log of 2, or you can write it as the log of 2 to the log of x, but that's pretty much all you've got. And let's verify that it doesn't match any of those. So for example, let's pick x equals 5 again. Let's suppose that x equals 5. And let's check. What is the log of 2 times the log of x? 0.2104. Put this over here. Okay, so 0.2104. And let's check each of these in turn. Let's check the log of 2 times 5. That's 1. Let's check the log of 2 plus the log of 5. That's also 1. Let's check the log of 2 plus 5. 0.845. So this is the value of our given expression when x is 5. Well, when x is 5, the value of A is 1. When x is 5, the value of B is 1. And when x is 5, the value of C is 0.845. And I pretty much have to conclude that it can't be those, so it has to be D, which is in fact correct. Interesting technique. And again, you can use that to verify that the correct answer in 11D is also none of these. Now, number 12, we have the natural log of 2 times x cubed. And remember, 2x cubed versus 2x cubed. These are different. What we have here is the natural log of 2 plus the natural log of x cubed, which would be the natural log of 2 plus 3 times the natural log of x. And that would give us D. Number 13. And this is xy to the 1/2 power, and as we've seen in class a few times, the 1/2 needs to be multiplied by the entire sum. Now, 14 and 15, a little tricky to do on the calculator. Let's go ahead and see why they're tricky to do on the calculator. Okay, they ask us for the domains and ranges of things. And the first one is the natural log of x minus 0.2 minus 0.3. It's the zoom 6. And it looks just like our basic, zoom in once, our basic logarithm graph. And if I was in trace mode. So the graph doesn't really start. You see that there's no y value here. There's no point on the graph that's associated with this at 0.15, but there is one at 0.21. So the fact that there's no y value associated with 0.15 rules out this one. I'm pretty sure there's no graph out here to the left. You could rule out this one and this one. And you could also rule out this one because this would not include 0.21, but 0.21 seems to be on the graph. Alternatively, this is y equal ln x that's been shifted right by 0.2 and shifted down by 0.3. And if you remember, the domain of this guy was 0 to infinity, and the range was all real numbers. So if we shift this to the right by 0.2, what was 0 to infinity now becomes 0.2 to plus infinity. And the range is still the same thing. Now in this one we have the graph. Again, we can look at this as y equals e to the x that's been shifted left by 0.2 and shifted up by 0.3. So the graph of y equals e to the x looks like this. Now if we shifted left some, you can see what was at 1 would go left. And if we shifted it up, and again the domain for this is R, and the range is 0 to infinity. And the range is affected by being shifted up by 0.3, and it becomes 0.3 to plus infinity. And again, there's various ways of figuring this out.